Hi, I'm going to talk about how the binomial distribution can be used to derive the Poisson distribution. I have viewed a few other sources that I list at the bottom, one on YouTube and one that was a blog, because I was really curious how the Poisson distribution gets derived, and I'll go through that. First I want to introduce my key. So whenever you see the letter N, that represents the number of trials, as in the binomial distribution. Whenever you see a lowercase p, that's the probability of success of an individual trial. Q is the probability of a failure in an individual trial. When you see X, that's the probability, that is actually the number of successes or events in a given space or continuum, like in time or area, of a number of events that you see in the Poisson distribution. But in the binomial distribution, that's the number of successes that you see, which I'm going to break down the Poisson distribution into looking at successes as the number of events that you see over an interval. When you see P of X, that's the probability to have X successes of events, to have a certain number of successes or events. Whenever you see lambda, that's the expected number of events over a continuous small interval or section of area. And that's part of the Poisson distribution. That's basically our expected value that you expect to see. When you look at the whole thing and you look at the number of events and you were to divide it evenly, that's what lambda is. That's the number of events you'd expect over a smaller area than the larger area. When you see Euler's number, E, that's Euler's number, that's 2.718281828. That is a special number that I talked about in one other video. Whenever you see n factorial over n minus x factorial, that really is the number of different ways to organize items that you pick from n items. And that's the number of ways that you can have those items organized. So it's a permutation when you see that. The binomial distribution I've gone over in a couple of videos, but basically that is the probability of getting a certain number of successes out of a certain number of trials. When you know the probability of success and the probability of failure, and you can only have either success or failure. You can't have like a number like 1 through 10 and you don't know which number it's going to be. No, it's actually got to be success or failure. And whenever you see n, choose x like this in parentheses. Notice there's no line, there's no numerator and denominator. This is actually kind of like a function. It's basically picking x items out of n items, and it's the probability or the number of ways of having a certain collection of items, even though you picked it out of a bunch of items, which would be n, the number of items. Whenever you see this is the formula for the Poisson distribution. So the probability of having a certain number of events in a certain space, like a certain interval, if you're thinking about time in one dimension, what's the probability of having 3 events or 4 events? That's what x is there, the number of events. You raise the number that you expect to have to the number that you're looking for. You divide by the number that you're looking for, factorial, and you take it times Euler's number and you raise it to the expected number of events minus the negative expected number of events. So basically this Euler's number raised to the negative lambda is actually in the denominator, if you think about it that way. And E is a special number. What E can also be thought of as taking 1 plus or minus a certain value over n and raising it to n, but that's as it approaches infinity. So as it approaches infinity, you get e raised to the plus or minus r, depending on what this was here. And that's used in continuous compounding, like if it's infinitely compounded, which I don't know that occurs a lot with money, but in nature, if you think of a plant growing up, as the plant grows larger, it can probably grow faster, right? So a plant doesn't just start growing faster when you get to the next year. It's always growing, right? So as it grows, it can grow a little bit more and more and more. So that's the idea behind infinitely compounded interest or infinitely compounded anything like growth. You're basically taking one and you're adding a certain rate to it, but you have to divide by whatever the interval is that you use. And that interval could be 6 months, 3 months, it could be a fraction of a year, and you could be given a rate for a year, for example, up there. And that uses this same kind of reasoning as n approaches infinity. So now I'm going to talk a little bit about the Poisson distribution and the binomial distribution. So for the Poisson distribution, to contrast it with the binomial distribution, you're using integers for x. Okay, well you're actually using integers for both. But over the sample, over the space, the number of possible things that you could get, you're using, like if you're using cards, you have 52 cards, for example, that's 52, n is 52. But what if you're looking at like over the span of 1 second? It could be anywhere in there, right? So it could be like 1/10,000th of a second, it could be anywhere in the middle. You don't know, right? So trials are countably infinite. So it's like taking 1 second, for example, and breaking it down to milliseconds, microseconds, and even less than that. You're looking at a continuous time frame, okay? So that could be infinite, right? And when we use E, it does become infinite. So trials are countably infinite, allowing for calculations of the probability of X events over spans of area, time, volume that are rare. Those events are rare, and they occur independently. Now this is really important. They have to occur independently. So if it's one second before the next second, there can't be like a change in how frequent those events occur based upon the second before. They have to be independent, okay? So going back to the binomial distribution, well first, actually I want to introduce an example here that I'm going to use as a framework for deriving the equation, but conceptually. So let's say that you have an agar plate and you have a bunch of bacteria on it. You have 400 bacteria on a 100 centimeter squared plate. So you have 100 centimeters squared on this plate. And if you just look at 1 square centimeter, what's the probability or what's the expected number of bacteria that you would have in 1 square centimeter if it's if it's 100 square centimeters that you have on the plate? If you have 400, you divide by 100, you get 4. So you would expect to see an average of 4 bacteria per square inch, right? So in this example, you see 4 of them there. Now let's zoom in on like 1 micron of that, which is actually 1/100 millionth of a square centimeter. If you look at 1 square micron, there's your bacteria. And let's just say the bacteria are like 1 micron in length. So it's difficult to get 2 of them in there because they're really rare, and let's just say these bacteria don't divide. So you're probably only going to have a success or a failure if you look at 1 square micron. It's either there or not there. You don't have 2 or more. You just have 1, or you have none. And that's the idea. And because the binomial distribution, as a pun, you can say it's binomial. Bi meaning it's just success or failure. Even though binomial actually doesn't come from that. Binomial actually comes from a guy by the name of Blaise Pascal. He came up with a triangle that shows if you take and you're adding like x plus 3 and you're raising it to a power, what does it look like when you expand it? And he actually figured out what the coefficients would be, and it would follow that triangle. Well, this same kind of math, the combination math, n choose x, was used in that. But we're using that for probability. for multiplying that times a specific sequence of events, successes and failures, to find all the ways to have successes and failures and still have the same number of successes out of those trials. Anyway, going back, so if we zoom in, we get one micron width bacteria for our example here, so that we can explain how this works. So the probability of X, like 4, that's going to be higher than all the other probabilities that you could get for numbers, or that, or the one adjacent to it. Just simply because that's going to be the most common, and that's what you expect. But what if you want to find the probability of having 5 bacteria, or 6, or 7, or 8, or 9 in that square centimeter? Well, that requires some math, right? And a lot of times you want to know, like, what's the probability of having this many events in this time space if it's really random? And that could be a way to test, actually, whether it's really random, because you would expect it to be random, right? But if it's not, then maybe something's causing it to happen that's based upon what happened before. And so when you're doing hypothesis testing, this might help you figure it out. So this holds true, the Poisson distribution holds true if 2 events can never occur in exactly the same trial. And this is unlikely to occur in this example. You're not likely to see 2 bacteria if they're not dividing and they're all spread randomly across the plate. You're probably not going to find in 1 micron, which is 1/100 millionth of a square centimeter, you're probably not going to find 2 bacteria next to each other very often, and probably not at all, maybe not at all. So that's the conceptual basis for this, is they have to be very well distributed and rare enough if you're using this small area here. Okay, so in this example, this small area is 1 micron, for example. Later, that's infinitesimally small. For the Poisson distribution, it uses an infinitesimally small, like dx, basically. If you know calculus, that's the smallest amount you could ever get, right? If you're going along a continuum of time, for example. So that'd be 1 centimeter divided by 1 micron, and that's how you get, so because that's the 1 centimeter. We're going to use 4 for lambda here. Lambda equals 4. So that's the basis there. That's 1 centimeter. But then now, if you're going to use the binomial distribution, we might use 1 micron, because it could be a success or a failure. Because you're not going to have 2 of them. You're just going to have 1 or 0, 1 and 0. And that's the idea behind it, just like flipping a coin, heads or tails, right? So when you do that, you get 100 million. That would be our n value. However, if you try to plug this into a calculator, you're never going to get an answer. It's just going to, it's not going to give you an answer, because even in Excel, if you use a spreadsheet and you try to find the highest number that you can do a factorial for, a factorial is multiplying. So you're taking n, and then you're taking n minus 1, but you're going all the way to 1, basically, and you're multiplying those values. You can't do that with 100,000, 100 million in a calculator. It's not going to do it. So there has to be a better way to do this, because if you want to make a calculation, it has to actually be realistic and tangible. At least you have to be able to do that, even with technology. And so that's the idea behind the Poisson distribution. Because over the span of a second, you could have like 1 microsecond, or like 500 microseconds, somewhere in the middle, right? Or somewhere here, actually, probably. And you want to be able to figure out what the answer would be. And that's just 1 point out of a number of points within that span. But if you're going to actually use the same kind of math for the binomial distribution, which is exact, the probability of having, because you could have that one event in any of those little spaces, those dx's, that's a lot of possibilities, right? But there is a way to boil it down to this formula right here. And I'm going to get into how to do that, starting with the binomial distribution, because the binomial distribution is for sure. It's for sure, but you can't do it for higher numbers on a calculator, even in Excel. So you end up with 4. You end up with 4, which is lambda. That's because there was a 4 in a centimeter. But then what's the probability of having it in this little space right here for an individual trial? The probability is 4 divided by 100 million. So that's so small, you're not going to expect to see more than one event. So that's why we can use the binomial distribution. Then we can do some math as we approach infinity, because we want to look at a continuum. We want to look at the whole space, every little bit, and find out like how many different ways are there to have these points over that whole span. Just like with the coins. Because if you have, say you want to find the number, say you want to find the probability of having 3 heads out of 10 flips, right? Well, these 3 can be organized over this whole span. So you could take 10 factorial, you could divide by 10 minus 3, and then take that factorial. Then you can take and divide that by 3 factorial also, the numerator, divided by basically 7 factorial times 3 factorial, and that will give you all the different ways to have heads out of 10 trials. Then you take that and you multiply it times an exact situation, which would be having 3 heads at the beginning and then having 7 tails at the end, which would be all the failures, right? And that's what we're really doing here. We're taking successes and then we're taking it times failure. If you do that, you find an exact probability of having those 3 heads in any order, right? We want to do that here, but we're using this little area here. And we're looking at all the little areas in 1 centimeter, and we want to find the probability of having those 4 successes, right, out of the 100 million, right? And so if you're even thinking about this as in phone calls, like the probability of having a certain number of phone calls in a certain span of time, if you work at a call center, you can use the same kind of math, because you don't know what millisecond you're going to get a phone call at, right? But you're just looking at the overall probability in that span of time, which is on a continuum. So this is the binomial distribution, and we're basically taking it to the limit of infinity. So it's a limiting binomial distribution. So to start out with, though, with a regular binomial distribution, you have the total number that you're drawing out of, if you're thinking of cards, for example, and you're dividing by n minus x factorial, like I said, and then also dividing by the number of ways you can organize them in that sequence of out of all the trials, how many could be successes, how many different ways can you do that, times the successes raised, times the probability of success raised with the successes here, times the probability of failure raised with the rest of them, which were all failures, and that's your probability. Because the law of probability says if events are independent, one event is not affected by the other event, you just multiply to find the probability of having whatever you're expecting. So the next step would be to break this n factorial down. So what is n factorial? Well, you're taking all those numbers, we're actually taking n factorial divided by n minus x factorial, which I show over here. So you want to take that and you want to break it down into one line. What does that look like? Because we're going to actually divide out, we're going to prove that this value divided by that value is actually 1 as you approach infinity. To do that, we got to break it down into n times n minus 1 times n minus 2, all the way down to n minus x plus 1. And that's what we're really doing. Because say you have 10 items, and you have 3 for x, for example. You're going to want to take 10 times 9 times 8, because that's 3. So the first item, you have 10 possibilities to choose from. Then you have 9 possibilities to choose from the remaining 9, and then you have 8. But you don't care about the rest of them. You only care about these 3, right? So in a permutation, you have 90 times 8, that's 720. You have 720 ways to choose. If you have 10 items and they're all unique, you have 720 ways to actually have those 3 cards in your hand, for example. So that's the idea behind this. So we end up with n times n minus 1 all the way to n minus x plus 1. When we do that, this is what it looks like. We don't know how many we're doing because this has got to be adaptable to any situation where we pick any number for x. So that's why we have to put it in this format. Then we divide by x because that was x factorial. Then we take it times the probability. Now remember I said the probability for our situation here where we're looking at 1 square micron, that's 4 out of 100 million sections out of this centimeter here that we're looking at success or failure. So when we do that, we can actually substitute the